I like the new picture, Cole.
Oh, thank you. I had to put that up there because Noah and I are now in a competition for who has
Ah,
best profile picture.
oh, that makes me nervous on a variety of levels. That should be interesting. So cool. So where is so who's the dude? Is that Jackson?
That's George Boole.
George, that's George Boole. Oh,
Mm-hmm.
that is awesome. Oh, well then you win.
Yeah, I had to
Having
do
not seen
something.
the competition, you win.
I don't know if he knows that we're in a competition yet. It's
Oh,
not
well,
been
that's okay.
formally.
Just don't tell him. You'll still win. And I'm sure Alice and Jaden will stay mum on the point. So that's very fun. I like that. Where'd you get the George Boole image? Is that like from Wikipedia or something?
I just found it on Google. I looked
Yeah.
up George Boole with sunglasses.
Somebody had already put the sunglasses on for you?
Mm-hmm.
Well, how convenient is that?
Yeah.
And then you just had to provide the background?
Yep. Just add the background on there and
Nice.
boom.
Nice. I like it. I like it a lot. Very cool.
Way too much free time.
Yeah, no, I understand. It's like Cole making, memes out of my face during class. So, so people are coming in slow today, I suspect. Some people might have been up late working on the homework. Judging from my mail spool, there were a lot of late questions. Okay, well, it's 9:15. Let us commence. Does anybody have any questions about what we've done so far before we do the coin change example, which will be by a fair margin, I think the most complicated proof that we have done all semester. Like it's a big proof with a lot of pieces. And I will try to keep the big picture clear as we go, but it's really easy to get lost in the details of this. And I've got a handwritten version that I try to scan and post as well in case you find that easier to track than having it happen live. Yeah, so are there any questions about anything before we start that? Okay, well then I think we're going to start that. So like I said, this is a complex proof. It's going to use pieces from just about every chapter that we've done. So this is one of these places where you know, everything comes together and we need all of the parts to make this work. But we get a pretty cool result. So it's a neat thing to do, but it's not a trivial thing to do. And it's likely to take more than just one class period. So I wouldn't be surprised if this dribbles into Friday and possibly even takes up a significant piece of Friday. We'll see. This is similar to exercise 12.14, and there is also an example of a similar problem in the chapter, but I'm going to do one, a separate one, just so you have yet another example of this kind of thing. So the thing I'm going to do here is the rather odd claim that any amount, so let's say any integer amount, that is at least 12 can be made with some combination of 3 and 7 cent coins. So if we live in this odd universe where the government produces 3-cent coins and 7-cent coins and nothing else, a reasonable question is, can we make all of the numbers? Like, or does this mean nobody can charge, I don't know, 45 cents because there's not a way to make 45 cents out of 3 and 7-cent coins? And it turns out that with 3 and 7-cent coins, we can make anything that's 12 or higher. There's some small things we can't make, like we can't make 4, right? There's no way to make 4 if all we have is 3-cent coins and 7-cent coins. But once we get to 12, from 12 and up, we can make everything, okay? And that's the claim here. That's what we're going to prove, is that we can make anything that's at least 12 using 3-cent coins and 7-cent coins. The problem in the book, which will be part of the next homework assignment, is that anything greater than or equal to 14 can be made with 3 and 8-cent coins. We can, if you understand this, hopefully you'll be able to do the proof in the homework. That's the goal anyway, is that this will get us there. But it's a big, complicated proof. Like the write-up in my notebook goes on for 1, 2, 3, 4, 5, 6 pages in my notebook. So 2, 4, 6 pages in my notebook. Now, your proof that you would turn in doesn't need to be that long. There's me sort of like talking and explaining things and doing some examples. I mean, so there's probably at least 2 pages of this is just Nick babbling on about, you know, trying to explain why I'm doing what I'm doing, whereas you could just like cut to the chase and get it done. But still, it's going to be a long write-up. I mean, there's just no 2 ways about it. It'll be, I would guess, the longest write-up of the semester so far. So it's a big-ish thing, okay? And so, you know, and it's also, because it's long, it's easy to forget where we are and be uncertain about, like, well, why are we doing this part? How does this relate to the thing that we're trying to accomplish? And so definitely as we go through, feel free to be like, great, I understand what you just did, but I don't know why you did it. I don't know how this fits into the story that you're trying to tell, the proof you're trying to assemble. So definitely ask those kinds of questions, because I think it's important that you understand why things are happening and how the pieces relate, as well as like that you understand the individual pieces, okay? So questions about any of this so far? Okay, then proof. So one question is, how do we formalize this? So this says that for anything at least 12, we can make it out of some combination of 3-cent and 7-cent coins. So if I came to you and I said, you claim this is true, and I came to you and I'm like, well, I'm not convinced. Show me that it works with 41 cents. Then I would expect you to be able to tell me, oh, if you use, I think 5 sevens is 35 and 2 threes is another 6, and that would get us 41. So your answer could be, hey, if you use 5 7-cent coins and 2 3-cent coins, that makes 41. And then I'd be like, oh, okay, that's cool. Well, how about, and then I could, keep giving you other numbers, right? But I would want, in some sense, the proof of this. It would be good if you could show me, well, how many 3s and 7s there are. And this hopefully maybe sounds a little bit like the divisibility problem, in that we were asking, well, like 3 times what is 4 to the n minus 1, which suggests that this would formalize as some sort of existence. So this formalizes as P of n is, there exists, and I'm going to use little p and little q. Wow, that was a weird exists. In the integers, or in the natural numbers, because you can't have anti-coins. You can't have like -3 7-cent coins. So we've got to have 0 or more coins of a given type. So there is a p and a q where n is 3 times p plus 7 times q for n at least 12. Okay. So this is how we're going to state the problem, formalize the problem, is that for all n at least 12, this exists statement ought to be true, namely that there should be some p and q where 3p plus 7q, so p is the number of 3-cent coins and q is the number of 7-cent coins, so that 3p plus 7q gets us the value that we're after. So in my example, if n was 41, q could be 5 and p could be 2. And then 6 plus 35 would be 41, and we would have shown it for that particular n, but we want to show it for all the n greater than or equal to 12. Are there questions about the setup? Okay. Now, I'm going to draw a picture of what the overall proof is going to look like and talk about that for a bit, and then we'll actually go on to the proof. So the overall structure is going to look something like this. To prove for all n in the natural numbers where n is at least 12, we're going to do the base case, namely n is, and in this case, the base case is going to be 12, which is sort of weird, right? I mean, whereas for most of these, the base case is 0, or maybe it's 1. In this case, it's going to be 12, because we're saying this is true for n at least 12. So we don't know that it's true for smaller n. In fact, it isn't for some of them, like 11, the next smaller number, can't be made out of 3s and 7s. So the smallest we can start with turns out to be 12. Now, why do I know that? Because I worked it out beforehand. For these coin problems, one of the tricks is always to figure out, well, what's the smallest number? And usually that's done basically through some trial and error. You kind of, try numbers until you get somewhere, and you're like, oh, does it work from there forward? No, it doesn't. We got to go up a little higher. Oh, okay, it works there, and it works everywhere else. Okay, good, we're done. And we'll see later on some stuff that will help us understand why 12 might have been important here. So, but you can just take it as it came from on high. So then we're going to do the base case, and we'll also do the induction step. Namely that P of n implies P of n plus 1. Okay? Now, one of the things that's going to make the structure of this complicated is we will end up splitting this up into two pieces as well. So it turns out that when we assume P of n, we'll have something that looks like n equals 3 times p hat plus 7 times q hat. So assuming P of n, we'll be saying, well, there is some value for p hat and q hat, where if we have this many 3-cent coins and this many 7-cent coins, that'll give us n. So that we have a way of constructing n out of 3-cent coins and 7-cent coins. And then, given that knowledge, we'll then figure out how to do it for n plus 1, okay? Turns out that the getting from this to n plus 1, we end up having to split this into two further cases. So we're going to have a case down here where p hat is at least 2, and a case here where q hat is at least 2. And it turns out that we'll have a little side proof that says that either p hat is at least 2 or q hat is at least 2. So we know one of those is true. Possibly both of them are true, but we know that for any n at least 12, at least one of these is true. Okay. And that allows us to do proof by cases, which is theorem 4.6. And I'll come back, maybe I'll say something about that now. I was going to come back to that later, but let's actually talk about that now. Let me go to a different color. I'm just going to sort of sneak this in here because I want to make sure that we've got all this on the same page. So we didn't talk a lot about 4.6. I mentioned it. I think we talked about it a hair, but we didn't say a lot about it. Partly because in chapter 4 we didn't really have a good place to use it. Well, now we have a good place to use it, so we get to come back to it. And 4.6 says, in fact, I mean, one of the things that's a little complicated about 4.6 is it works for an arbitrary number of cases. We're going to do 2 here, but it could be 4 or 6 or, a billion. I mean, obviously, if it's a billion, then that's hard to work with, but we are not limited to a particular set of cases. I think in the book they do it with 3 just to sort of make the point, but we will actually only need 2. And so 4.6 says, if you know P or Q, and there's a lot of P's floating around here and Q's, but this is these P's and Q's are just in the statement of 4.6 and have no connection to capital P here or little p and little q down here. So P or Q and P implies S and Q implies S implies S. So what this says, and like I said, in the book, there's P, Q, and R. So it's longer, but we only need the two pieces here. So to prove S, what? Cannot spell. I think it's a sign that online teaching is eating my brain. My spelling seems to have collapsed this week. So to prove S, we need to prove three things. We need to prove P or Q. We need to prove that P implies S, and we need to prove that Q implies S. So if we want S, one way to get there is to have two cases, P or Q. We need to show that one of them is true at all times, and that if P is true, S will be true, and if Q is true, S will be true. So this is like the even odd business that we did back in chapter 5, I think it was. So if you know that a number is either even or odd, and that if it's even, you get there, and if it's odd that you get there, then you get there, okay? Then you have that S is true. And in this instance, we know that, we will know, we haven't shown it yet, but we will know that P hat is at least 2 or Q hat is at least 2, which means that coming down here, let me change color. Coming down here, we have P hat at least 2 implies capital P of n plus 1, and Q hat at least 2 implies capital P of n plus 1. So if we know that one of these is true, P hat at least 2 or Q hat at least 2, and we know that both of them get us to P of n plus 1, then these two things combined get us to P of n plus 1. So these two things get us here, these two things get us here, and we have the complete proof. But it's in now 4 parts, which is a way more complicated structure than we've seen before, right? We're moving from writing proofs that are sort of not even quite short stories, like they're just little, images, scenes, to writing something that's got 4 acts, right? We're going from a little scene to a whole play in some sense, with multiple parts that have to kind of work together to get to the end. So this is a substantially more complicated structure than what we've been doing before. So before I get into the actual doing the proof part, does anybody have any questions about the structure? Because the structure is kind of like a lot, okay?
How do we get the 2 from the base case, or do we just pick a random number?
These 2's here, the P
Yeah.
hat. Well, so that's a great question. That's magic I have not yet shared.
Okay.
So it is actually a bit on the magical side. It's actually one of the weirder parts of the proof, is that knowing what numbers go here is kind of a trial and error poke at the thing and see if you can figure something out. But it will be, we'll sort of cover what you're doing when we get to that part. At this stage of the game, it is entirely mysterious why those would be 2s. I haven't, you have no information that would help you understand why those would be 2s right now. So good question. I mean, actually great question. Shows you're paying attention. Go, Abdi rocks. Other questions?
In the case of using axiom 4.6, is P or Q the P hat greater than or equal to 2,
Yes.
and S is P of n plus 1?
Correct. Good
Okay.
catch. So let me actually make those labels here. So here, this would be the P in that guy there. And this is the Q. And I won't draw the squiggly line. And then, yeah, the P of n plus 1 is going to be the S. That guy there. I don't know if that'll be super confusing if somebody looks at this later, but whatever. But yes, so the P and the Q here are these two guys, and the S is the thing we're trying to prove, which is P of n plus 1. And so we need to show P or Q is true. So we'll have a little proof of that later, and we'll need to show that P hat at least 2 gets us to n plus 1, and that Q hat at least 2 gets us to n plus 1. Does that make sense? Any other questions?
So are
Go ahead.
you like doing 4 proofs within this one proof?
Yeah. So we're doing, I mean, depends on how you want to count things, but this is a little proof, right? The base case is a little proof. Let's see. If we change to green, so we have the base case is a little proof. We will need to do this as a little proof. We will need to do this as a proof. We will need to do this as a proof. And there's going to be varying amounts of connective tissue, sort of, English language verbiage that sort of joins these pieces together so that we don't just end up with 4 random statements without any idea of how they connect to each other. So there's at least 4 little proofs plus this sort of joiny up stuff that we need to connect the dots, which is part of why this is a long write-up and why it's a complicated thing to present. And so it's why I'm spending all this time, like we haven't even started the proof really, and I'm spending all this time because I want to make sure we understand what the structure is. Otherwise, watching me do this is going to it's going to feel like I'm just shouting random things at you. And you don't know why are we doing this? Well, we're doing this because it's, this part of this tree, right? And so we need to have some understanding of this big picture so that when we do these pieces, you have some idea why we're doing those pieces. Does that make sense? Questions?
Yeah, thank you.
No problem. Anybody else? Anything else? Okay. Well, let's rock on. Okay, so now we've talked about the overall structure. So now we're going to come back to actually, the induction proof. And so I'm going to make a new slide and switch back to black. So the goal is to prove that there exists P and Q in the natural numbers such that n equals 3 times P plus 7 times Q for all natural numbers n at least 12. So there's our goal. So first, let's do the base case because the base case is actually easy. The least of the awfulness of, well, I mean, none of it's awful, but it's the most straightforward piece, arguably, of this whole thing. So the base case, which I forgot to write the word case, base case is n equals 12. So that tells us that we have exists PQ in the natural numbers where 12 equals 3 times P plus 7 times Q. And as we've seen on the divisibility problems, this follows by exist introduction 9.28 from 12 equals 3 times some expression E plus 7 times some expression F, where E and F need to both be natural numbers for this to work. So can we just, by eyeballing it, come up with a value for E and F that make this true? Question for the room.
E4 F0.
Yeah, exactly. Right? So this follows by arithmetic from E equals 4 and F equals 7, or 0, sorry, i.e. 12 equals 3 times 4 plus 7 times 0. And so we're good. This is true. And since both 4 and 0 are in N, this completes the base case. And we do need to check that 4 and 0 are in the right range. We don't want negative numbers because that would be essentially anti-coins. Like I have -2 nickels. What does that mean? And we don't want fractions. You can't talk about, I have 2/3 of a dime. I mean, you could physically make 2/3 of a dime, but I don't think banks take those. So that would be a bad plan. Josh has a question.
Yeah, why do you have a follows from symbol for the arithmetic step?
So that's a great question. Why do I have a follows from instead of an equivalence? So this is saying that this implies that. But they might not be logically equivalent. In particular, there might be more than one way to do this, to solve this equation. This equation might have multiple answers, in which case, so as an example, let's say the equation I'm trying to solve is x squared equals 25. Well, that is not equivalent to x equals 5. No, bad. Because it turns out that this actually has two solutions. So really this is x equals 5 or x equals -5. So actually this follows from x equals 5. So that would be one of the weakening strengthening rules from chapter 3. And so in general, when you've got an equation like this and you have one particular solution, it's not that this is, unless you know this is the only possible solution, you don't get an equivalence, you get a follows from here. And there are almost certainly other solutions to this. In particular, if we allow for fractional and negative numbers for E and F, there are probably a lot of solutions that we could put here. They are not helpful solutions in our case because we need E and F to both be natural numbers. But in sort of the big picture case, there could be many possible solutions here. So I'm saying this is not equivalent to this, but this follows from this. That this gets me there. And that's all I needed. I just needed to show that something got me what I was trying to prove. And in this case, 4 3-cent coins and 0 7-cent coins gets me to the target that I was trying to get to. Does that make sense? Questions?
Yeah, that makes sense.
And that's an
So
oh, go ahead.
if there was only one solution, would it still be okay to use follows from?
Right, because P equivals Q implies P implies Q. So if all you need is P implies Q, and that's actually all we need here, we've already lost equivalence in the first step. Since all we need is implication, if we have equivalence, the fact that it gives us implication, that's fine. We're okay with implication here. So we don't need to sweat it in this instance. And this is a rule from chapter 3. I'd have to look up the number, but this is one of the rules from chapter 3. So does that make sense?
Yeah.
So those were great questions. So thank you. Other questions? Okay. So this completes the base case. So if we back up, this we have done that part. Ching. And we still have all the rest of this to do. Are we with me on the base case proof? And are we with me on the structure? And I can back up to that other slide if that would be useful.
Nick,
Yes.
so you mentioned earlier that, they both, that we're looking for a natural number
Mm-hmm.
that's there. But I mean, couldn't we just say any positive integer because it's a coin problem? Like, because it's not possible that we could have a fractional number or a negative number, we would just say z plus or something like that?
Well, you wouldn't want z plus because you do want to allow 0, right? Z plus wouldn't allow 0 here.
Right. That makes sense.
So
Okay.
you do need the natural numbers and not positive integers because you want to allow 0.
Okay. Yeah, no, that makes sense.
Was that it? Did that answer the right question?
Exactly that.
Bingo. Go team. Other questions? Good question. Great questions today. Full marks to you folks. Okay. So we've done the base case. Now we get to do the induction step. So I'm going to make a new page. So now we have the induction step. Namely that Pn implies P of n plus 1 for n at least 12. So we're going to write this as, we're going to sort of do our formalization. So this is, there exists P and Q in the natural numbers such that n equals 3 times P plus 7 times Q, that implies that there exists presumably a different P and Q such, in the natural numbers, such that n plus 1 equals 3 times P plus 7 times Q. Which by 930 is true if and only if n equals 3 times p hat for some new variable p hat plus 7 times q hat implies there exists p, q in n plus 1 equals 3 times p plus 7 times q. Okay. And one thing we're doing here that we haven't seen before is when we've used witness like this in the past, there's always been just a single variable in the exists. So we had a single hat thing that got brought into the world. Well, here we have two exists, and you can see that it's legal and okay to just like make two hat things. And if there had been like exist 7 variables that made something true, we'd have 7 hat variables. And that would be fine. So this is just saying that if we know that 3p hat plus 7q hat is n, then we want to find p and q that make n plus 1 work. So if we know that p hat 3-cent coins plus q hat 7-cent coins gives us n, can we then find p and q that give us n plus 1? That's what we need to prove now. Okay. Questions about that? And this looks pretty similar to the divisibility stuff so far. So we'll assume the antecedent. Namely that n equals 3 times p hat plus 7 times q hat. Okay. And prove the consequent. And so the consequent is there exists p, q in the natural numbers such that n plus 1 equals 3 times p plus 7 times q. And then by 9.28, this follows from n plus 1 equals 3 times sum e plus 7 times sum f. So there's got to be some expression e and f that makes this true. And then we can use our induction hypothesis. And we can replace n here with the 3p hat business. So we get 3 times p hat plus 7 times q hat plus 1 equals 3e plus 7f. Whew. Okay. Now, so far, this has been reasonably straightforward. This is similar to how we did the divisibility problems. We needed to show that this implies this. They're both exists. So we use witness to get rid of the exist on the left. Then we assume that antecedent, and now we need to prove the exists on the right. And we use exist introduction to get rid of the exists on the right. And then we get down to here. And in the problems before, we were then able to just do a little algebra and solve for the expression. But it's more complicated here because we have two expressions. We have E and F. And we can't just do a little algebra in that sort of light way that Nick says, like it's going to be easy. We can't just do a little algebra and solve for E and F. We've got this weird situation where we have these two values that we have to find solutions for. And it's like, okay, what do we do here? And the interesting part in some way is this 1 here. Like if the 1 wasn't here, we could say, oh, well, we're done, because E could be P hat and F could be Q hat. The two sides would be equal. Hurrah! But we can't do that because the 1. Sad. Much sad. So what do we do about the 1? Well, it would be cool if we could write 1 as a combination of 3 and 7. If we could write this as 3 times something plus 7 times something, then we could algebra everything together and we'd have 3 somethings and 7 something on this side and 3E and 7F on that side. And E would then be however many 3s we had and F would be however many 7s we had, and we'd be done. So the trick now is to figure out, well, how can we write 1 as a combination of 3s and 7s? And we can't obviously do it with only positive numbers of 3s and 7s, because obviously, or even non-zero numbers of 3s and 7s, because 3 is bigger than 1 and 7 is bigger than 1. So, you know, if we just have integer number or positive numbers of 3s and 7s, we're going to be bigger than 1. So we've got to think about this in terms of having potentially negative numbers of coins. And that's weird, right? Because we can't have negative numbers of coins. But we can if we think about trading, not in the chapter 9 sense of trading, but trading just as like you and me, like trading, you know, Pokemon cards, to a reference from a million years ago. That if I give you a nickel, right, that's sort of -1 nickels for me. A nickel is leaving me. And if you give me a dime, that's a +1 dime for me. And so if I say I need quarters for a vending machine, but I've got a dollar bill and you have 4 quarters, I could give you a dollar bill. That's a -1 for me. And you can give me 4 quarters, and that's 4.25s from you. And I'm net 0, right? I lost 100 cents and I gained 100 cents. So I'm in the same place I was to begin with. You're in the same place. You gained a dollar bill, which was 100 cents. You lost 4 quarters, which was 100 cents. So you are even too, right? We both are in exactly the same place in terms of the total amount of money we have. But what we have is in different forms. I now have quarters. I can buy random corn syrup in a congealed form from a machine, and hopefully you don't mind having a dollar bill. Maybe it makes you happy to have a dollar bill. I don't know. So a question is, can we do some trading with 3-cent coins and 7-cent coins that would leave me up 1 penny? Can I give away some coins and get some coins in a way that in the end, I have 1 more penny than I had to begin with, 1 more cent than I had to begin with? Does that make any sense? And can anybody propose a simple trade with 3-cent coins and 7-cent coins, where if I give up a few and I get a few, I end up with 1 more cent than I had before?
You could give up 4 P's and gain 1 Q and 2 P, 1 Q and 2 P's.
Which really just means I need to give up 2 P's and get 1 Q. that if I give away 2 3-cent coins and I get a 7-cent coin back, I'm up 1. Right? Does that make sense? So if I come over here and I say, if I give up 2 3-cent coins, I lose 6 cents. If I get back one 7-cent coin, then I'm up 1 cent overall. Which, if I take this out of math land or out of English and into math land, what this tells me is that 3 times -2 plus 7 times 1 equals 1. So that I could put this in for the 1 here. And then I would get a certain number of 3-cent coins and a certain number of 7-cent coins on this side, and then that would tell me what E and F were. Okay. Now that's a lot that's going on, and that's kind of weird. So are we cool? Do we get that this is 1 and that I could possibly, since this is equal to 1, I could put this in for here, and that might give me some set of 3-cent coins and 7-cent coins? Questions?
I think it makes sense. I think it's confusing because it seems like you're only supposed to work with natural numbers.
Correct.
So I'm not quite understanding that.
And you're completely right. And so it's like, but yes, help, how, anti-coin problem. So the trick is, let's actually plug this in. And I'm gonna actually stay in green because this is where we're gonna have to do the split into the P at least 2 and Q at least 2 business. So we're gonna have to like come back here and do some tidying up, but I'm gonna actually run with this as if this is just gonna be the answer. And then we'll have to figure out kind of how we clean up. So let's just say, well, we know this, right? And this is clearly true, right? This is something you knew was true way back in elementary school. You could have, confirmed that. Once you knew about negative numbers and multiplication, you would have been good to check this. So we would have 3 times P hat plus 7 times Q hat plus 3 times -2 plus 7 times 1 equals 3E plus 7F. And now we'll join up the pieces here with a little algebra. So we got 3P plus 3 times -2. So this is 3 times P hat minus 2 plus 7 times Q hat plus 1 equals 3 times E plus 7 times F, which, and I'm running out of room here, this follows from E equals P hat minus 2 and F equals Q hat plus 1. So all of this would imply all of that, okay? And now we're going to get to Cole's uncomfortableness with the anti-coins here in a second. But if we just ignore for the moment the anti-coin problem, does the sort of the math we did to get from the black, the last of the black here, through this green to here. Does that math all make sense? Do people have questions about that math?
For your implication at the very bottom, do you just solve the equation or?
Yeah, I'm just saying that like one way to make this true is to say that E is P hat minus 2 and F is Q hat plus 1. Like if I just put P hat minus 2 and Q hat plus 1 here, that just in a trivial way makes that true, right?
Yeah, okay.
So I'm basically reading off the answer from the left-hand side to tell me what the expressions are on the right-hand side, which I could only do by replacing the 1. Like at this point, I couldn't do that. At the last line here that was in black, and man, if anybody out there has sort of color blindness where I'm just babbling on about green and you don't see green, you should definitely let me know. I have no idea how colorblind friendly my color choices are. They're probably not terribly, and I have no idea if there's somebody in their class that has trouble distinguishing these colors. But so definitely let me know. But at this point here, we couldn't just read off E and F because we didn't have 3 times something plus 7 times something. We had this plus 1 in the way. And by using the suggestion of 3 times minus 2 plus 7 times 1 from Justin, we were able to do this algebra and get this down to something that was 3 times a thing plus 7 times a thing. And then we could just read E off as P hat minus 2 and F off as Q hat plus 1. Does that make sense? Questions about that? Okay, now let's come back to Cole's general sense of unease, which is totally legit and absolutely needs to be acknowledged and dealt with. And the trick with the general sense of unease is if this is going to be our solution, actually I'm going to make even a different color. You go to blue. For this to be a valid solution for E and F, we need to know that P hat minus 2 and Q hat plus 1 are natural numbers, right? Because what are we shooting for? We're trying to find values for E and F that are natural numbers. That's the goal that we're getting to. So all the way through this, it's important that E and F have to be natural numbers. Well, this one's no problem because Q hat's a natural number. So Q hat plus 1, also a natural number, not a problem, okay? This one, however, is a little worrying because this isn't always a natural number. In particular, if P is too small, if it's 0 or 1, this goes negative and we don't have a natural number anymore. So this is only a natural number. So P hat minus 2 is only in N if P hat at least 2. So this is now tiny little letters at the bottom of the screen, and it's a super important thing. So I apologize if this has now been buried for lack of space on the board, as it were. But this is, so to go back to Abhi's question from a long time ago, this is where the 2 comes from. This is why one of our cases is that P hat is at least 2, because we can only use Justin's trick here if we know we have at least 2 3-cent coins. Because if we do have 2 3-cent coins, at least 2, then we can give 2 away and replace them with a 7-cent coin and be up a penny. Okay? But if we don't have a pair of 2 3-cent coins, we can't use this trick. So we have to only use this trick in a case where p hat is at least 2. Okay? So this is sort of the critical piece, is that this trick was nice, and we kind of knew that right here, and this is, I think, the thing that was causing Cole distress in some way, that because we had a negative number there, we could only do this if p hat is at least 2. Okay. So that's where that assumption comes from. And that's why when I said I would sort of, press this out in green and that we'd have to tidy up, this doesn't always work. We can only do this in this case that p hat is at least 2. So just barreling forward here, I sort of I'm in this weird state that sometimes this worked and sometimes I fall off a cliff and everything explodes. And so I'm going to have to clean up and basically, erase everything back up to this line here. And then we got to think about, well, what are our other options? If p hat is not greater than or equal to 2, is there another option we can take, another fork in the road that we can take that will work, and so that we don't go off the cliff if p hat is like 1 or 0, something like that. Okay. So let me think about how to frame this. Do we get the algebra that got us to here? Do we sort of get what we did by replacing the 1 with a combination of 3s and 7s, and that simplified down to this, and then we could read E off and F off and get that? Are there questions about that stretch of what we did?
I'm wondering, would you be able to have a 1 cent since it's a 3 cent and 7 cent world?
Right, that's a fair question. So when I say a penny, that's really badly phrased. It's not a penny. It's you have a set of coins whose value is 1 cent, or you have an exchange whose net result is to increase the amount of money I have by 1 cent. So like if I've got 4 3-cent coins and a 7-cent coin, that adds up to 19 cents. And you've got just a pile of coins. We don't really care how many you have. And if I give you 2 of my 3-cent coins, then I go from 19 down to 13. And you give me a 7, then I go up to 20. So net, I've gone up by 1 cent. Yes, there is no 1 cent coin. There's no penny. So when I use the word penny, that's broken. And I should stop doing that. But it's still the case that I have, in total, gone from 19 to 20. I've gone up by 1 cent by trading a pair of 3s for a 7.
Okay, so it's about the net value instead of like the actual. Okay.
Absolutely. So I didn't invent a new coin. My net value went up by 1 cent.
Okay.
And my phrasing was awkward there, and I apologize. So thank you for asking.
No problem.
No, it's good that you asked, because I don't think I did. I could hear myself making that mistake, and yeah. So, other questions about like this stretch here, this little L here in green? Now, if we buy this little stretch, are there then questions about the need for p hat to be at least 2? Do we get, and Cole, does this help with your concern that this is only going to work if p hat is at least 2? Does that?
Yeah, it makes a lot more sense now.
Okay, good. Are there other questions about the p hat at least 2 part? Okay.
This is going back to the Q is greater than or equal to 2. Where does that come into play? Because
that's the next slide.
Oh, okay.
Because yes, right. We had, if we back up, boom, boom, we had P at least 2 and Q at least 2, and we've kind of, this has been demagified. Boy, I just made up a bad word there. A little bit, but we haven't even talked about the Q part. So we now need to kind of clean this up and figure out, well, because we've got an assumption here that P is at least 2, but that's not always going to be true. So if P is less than 2, what do we know and what can we do about it? And it turns out, and that'll be the next slide, actually that'll be Friday because it's 17 after already. It turns out that if P hat is less than 2, but N is greater than or equal to 12, remember that was the assumption. Oh yeah, it's still on this slide. N is at least 12. It turns out if P hat is less than 2, Q hat will need to be greater than or equal to 2, or we can't get a value that's greater than or equal to 12. So P hat less than 2 will imply Q hat greater than or equal to 2. That's something we'll prove on Friday. And then it turns out we'll need to come up with another trade like this. So Justin came up with this trade that I'll give up 2 3-cents and I'll get a 7-cent and I'll be up by 1 cent total. Well, there'll be another trade where I give up some 7-cent coins and get some 3-cent coins so that I'm up by 1 cent again. And that in that case, I won't need the assumption that P is at least 2 because I'm not giving up any 3-cent coins, but I'll need the assumption that Q is at least true because I might be giving up at least 2 7-cent coins. And that's why we have this case split, is like, do I have enough 3s? Oh, I don't. But then I'll have enough 7s, so I'll do that one instead.
So then do we disregard the F equals Q hat plus 1 for now, or is that just?
Well, in fact, I'm going to essentially erase all of this that's in green, and we'll sort of figure out what our 2 cases are, and then we'll do them both. But when we come back to this, no, this is still true, right? That if P hat was at least 2, we can get rid of 2 3-cent coins, gain a 7-cent coin, and we've gone up by 1 cent. So we still need the Q hat plus 1, because in this case, we're getting rid of 2 3s, gaining a 7, and net we're up a penny. Not up a penny, up 1 cent. Okay. And that's 20 after, so I should probably shut up. This is super confusing. I mean, there's a lot going on. So definitely, I would encourage you to look through this again between now and Friday, and then we'll pick up Friday and sort of work out our cases more clearly, and then we'll do the 2 cases. That'll complete the induction step. That'll complete the proof. Whew, so much going on. Questions in the 0 minutes that remain? Awesome. You've asked great questions today. I mean, really, really great questions. Everybody, full marks. That has been awesome, and I really appreciate it. So I will see you all later. And if you got any questions, let me know. Ciao. So I wanted to save. Okay, now stop sharing. Add.
Oh, hey, Nick.
Oh, yeah? Go for it.
Random sidebar. Do you do any gaming at